In this lesson, you're going to learn about the median and the altitude of a triangle. We'll start by looking at the median of a triangle. And the median of a triangle is just defined as a segment from a vertex, we'll call this vertex A, to the midpoint of its opposite side. So here we'll call this the midpoint. We'll label it M. And that just splits that side opposite angle A into two equal portions. So I could say that this portion is congruent to that one. If I draw this segment connecting, that is now the median. Notice what happens when we draw three medians of a triangle. We start with vertex A over to the midpoint of line segment BC, vertex B to the midpoint of AC, and then finally vertex C to the midpoint of AB. These three lines intersect at a point which we call the centroid of the triangle. Looking at this triangle, we have that the centroid is point P. And we have an interesting relation that goes on. If we actually take the median of the triangle, so we're looking just in this case at BF, and we divide it into three equal portions, you'll notice that I can divide BF into thirds, and BP is actually 2/3 of the entire BF. So the property that we have here is BP is equal to 2/3 of BF. This is always the case, and this is the concurrency of medians of a triangle. The centroid of the triangle, so the point where these three medians intersect, is always 2/3 of the distance from each vertex. So similarly, we could break up AE into three equal portions, and AP would also be equal to 2/3 of that median, which is AE. So as an example, if BP is equal to 6, what we have is that 6 is equal to 2/3 of BF. So we can solve. Multiply both sides by 3. And we get 18 is equal to 2BF. Divide both sides by 2. And BF is equal to 9. So this entire median is 9. Divide that into three equal portions. 3 plus 3 plus 3 is the entire median. So BP was defined as 6, which means what's left over here for PF is simply 3. PF is equal to 3. And we're done. For this example, we're going to start applying the theorem that was just used. And I'm going to show you two different ways to approach this. The first way is just by using the theorem itself. And let's focus on the median BF to hopefully find the value for y. So the relation we have is that BG is 2/3 of the length, so 2/3 of BF. So let's go ahead and write that down. BG is equal to 2/3 BF. Now I can substitute. We have that BG is equal to 24, and BF is equal to, here we're going to have to add 24 plus 3y minus 3, since we have to account for the entire length BF, so it's BG plus GF. Now some cleanup work. 24 is equal to 2/3 times 24 minus 3 is 21 plus 3y. Notice how I use parentheses. If I didn't do that, I would have made a mistake of not distributing the 2/3 everywhere. At this point, I don't really want to work with fractions, so let's go ahead and multiply both sides by 3. And 24 times 3 is 72, is equal to 3 over 3 is 1, so we're left with 2 times the quantity of 21 plus 3y, which I can distribute the 2 to each term. So I get 42 is 2 times 21, plus 6y. Finishing up solving for y, we can subtract 42 from both sides. And 72 minus 42 is 30 is equal to 6y. So solving for y, divide both sides by 6, and y is equal to 5. Now, that's actually the longer way of solving one of these. And we can go through and do this for all of the other variables, but let's look at it a different way. If I know that AE can be divided into 3 equal portions, 1, 2, 3, and 2 of those portions are going to represent the length of AG, and one of the portions is going to represent the length of GE, well, each portion should then be the same as GE. GE here is 11. So what I have is 11 and 11. So, in other words, AG is equal to 11 plus 11. So 6Z plus 4 is equal to 11 plus 11. This is a little bit easier to solve. 6Z plus 4 is equal to 22. Subtract 4 from both sides, and 6z is equal to 18. Divide both sides by 6, and we get that z is equal to 3. I'll let you try it for the third side to see if you can come up with the value for x. You've probably not only heard the term altitude before, but you've probably used it a lot. And in particular, if you've ever been on an airplane, they talk about altitude as the height above the earth. So when we're talking about an altitude of a triangle, we're going to focus on the vertex and the opposite side. And in particular, you want this to be a perpendicular or 90-degree height. So what you can do is always drop a line from a vertex to the opposite side at a right angle. That is defined as your altitude of the triangle. So again, any of these triangles, dropping those lines from any vertex to the other side, and you get a right angle. Notice that over here from Q to S, well, that's already a right angle, so my altitude is just the side itself. But what happens if we look at a triangle like this last one, where Q down to S at a right angle would be somewhere over here. There's no really way to write it as a right angle. So what you can do is continue the side SR. Imagine that it continues, and drop the line at a perpendicular to its opposite side, SR, which is continued. That's okay. Now, these altitudes that I've shown you here make sense, but you can always turn the triangles too and look at altitudes of other vertices. So in other words, if I look at the altitude from S to its opposite side, again, it would just be drawing that line at a perpendicular 90-degree angle. This picture may look a little confusing at first, but what I want you to focus on is triangle ABC. That's the original triangle that we start with. What we've then done is we've drawn the altitudes of this triangle. So the first altitude, AF, and then the other two altitudes, BE, that happens at a right angle once we continue CA. And by continuing and making this line longer, we have the altitude CD. An interesting thing that occurs with altitudes is if you actually continue those altitudes, they all meet up at this point. And we call that the point of concurrency. It's the point G. So the theorem associated, concurrency of altitudes of a triangle, is that all of the lines containing the altitudes, so for example, AF, BE, and CD, when we continue them, they all meet at this point G. In this last example, I'm going to model something that you may see in your homework and questions that are asked later on. Question 1 states, well, decide whether the segment MS, so this segment here, is a perpendicular bisector, an angle bisector, a median, an altitude of this triangle. So what we have here is that angle KMS, this angle here, is congruent to LMS, this angle here. If you have congruent angles, so this angle and this angle are the same, then MS is a angle bisector. Angle bisector splits the larger angle into two congruent angles. In the second one, if KS is congruent to SL, then what we have is that MS meets its opposite side at exactly the median. That makes MS the median of the triangle. Lastly, if MS is perpendicular to KL, so I can draw my little box that indicates perpendicularity, then what we have is MS is one vertex down to the perpendicular of the other side. That's an altitude of the triangle. One thing to notice is that sometimes MS, that segment, could be both the angle bisector, median, and the altitude. It doesn't just have to be one or the other. So you do have situations where you'll have a bunch of things going on, but you need to be able to recognize them by the properties that are presented.